Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is count the number of complete components. So let's go to LeetCode and read this problem. So you are given an integer n. There is an undirected graph with n vertices numbered from 0 to n minus 1. You are given a 2D integer array called edges, where edges at the ith position, the value is a pair which has a and b, where it represents an undirected edge going from a to b or b to a because it's undirected, so both components are in each other's neighbors list. Now return the number of complete connected components of the graph. What are complete connected components? Connected components we already know. We have done a lot of problems like that. What is complete connected component? So they have said like a connected component is a graph. We already know that. But a connected component is said to be complete if there exists an edge between every pair of its vertices. What does that mean? Let's go over the first example right here. We'll understand that. So I've taken the first example. We are given 6 nodes, 0 to 5. So 0 to n minus 1. N is 6, so 0 to 5. Now these are the edges that represent basically an edge between 0 and 1, and it's undirected edge, so they both connect to each other. Now this is our entire graph, and you can already tell this is not a connected graph. It's a disconnected graph, but it does have connected components. This is one connected component, this is one connected component, and this is one connected component. So there are total 3 connected is that the spelling of connected bar? Like connected, 3 connected components, so 3cc. So what do we need to tell? We need to find complete number of complete connected components. So what are complete connected components? As we just read, so a complete connected component is a component where all the nodes are connected to basically every other vertices in that component. So basically, if you look at so first of all, is this a connected component? Is 5 connected to itself? Yes, it is. Is it not? Because there is just one node in this component, and a node is connected to itself. So simple answer, it is basically connected to itself. How about this one? So we'll go vertex by vertex. So how about 0? Is 0 connected to every other vertex in this connected component? So yes, it is, because so 0 is connected to 2, 0 is connected to 1, and there are only 2 other nodes other than 0 in this particular connected components. So that is why this one will also be a complete connected component. How about the third one? Well, here there are 2 nodes, but by the way, remember, we checked for 0. This is connected to every other vertices in this connected components. 2 is also connected to every other component, every other vertex in this component, and 1 is also connected to every other vertex in this component. So you can see like right here. So this is basically like a cycle. But how about this one, the third connected components? Is this also complete component? Well, it is, because there are 2 nodes. So 3 and 4, and you can tell that 3 and 4 are connected to each other. So 3 is connected to the only other vertex in this component. So it is connected to 4, and 4 is connected to 3. So that is why this is also a complete connected component. So that is why the answer here would be 3. The answer would be 3. Well, let's take an example of a connected component which is not complete. And you know what? We can make for ourselves right here. This right here. So if I remove this edge, so 2 and 1, so 1 and 2, that is the edge we are removing. And let's shift this right here. So we have changed the example. All right. So you can tell that this 5 is a connected component, right? We already discussed that this is a connected component and this is also a connected component. This was a connected component, the middle one. This was a connected component when we had this edge right here, because then 2 was connected to 0 and 2 was connected to 1. But now we removed this connection. That is why it is not a connected complete connected component. It is a connected component because all the nodes are, you know, part of the same component, but it's not a complete connected component. And the reason is, well, 0 is connected to 2 and 1, which means 0's neighbors are 2 and 1. 2 is kind of connected to 0 and 1 is connected to 0. But previously that was not the case. Previously our graph would have been 0 is connected to 2 and 1, 2 is connected to, if this edge was present, so 2 was connected to 0 and 1, and 1 was connected to 0 and 2. So earlier in the neighbors list of 2 and 1, we had 2 values, and even for 0 was 2 values. So if a component is complete and we are done making the graph, then you will realize in that connected component, every vertex and its neighbors list would be basically the size of all the nodes in that. So if the nodes in this are k, so the size of each neighbors list would be k minus 1. And that is exactly what we are going to check here. Let me note down the steps here that we will be doing to basically check if a component is a complete component. So first of all, we will have to find out these connected components, right? We will have to find out these connected components. So that will be, we will use, first of all, by the way, let's create the graph for this. So we will create the graph using the edges. So I'll create it right here so that I can write, you know, our steps on the right hand side. So graph would be basically this dictionary, and I'll have 0, 1, 2, 3, 4 and 5, right? So 0's neighbors are 2 and 1. 1 neighbor is 0, 2's neighbor is 0, 3's neighbor is 4, and 4's neighbor is 3, and then 5 neighbor is empty. All right, so it is empty, although it is connected to itself, but we will make sure that we are considering a single node itself, because it is connected to itself and it will be part of our value. All right, so when we count the complete components, it will be part of our value. So here you can see this is the graph that we created. We have already done it so many times, so you would know how you create this. Basically, you visit all the edges and then append both values into each other's neighbor list in our dictionary called graph. Now our first step would be, step 1 is actually done. So step 1 is create and fill graph adjacency list. All right, now step 2, sorry about this, that is not the right spelling of step, STEP, step 1. Now step 2 would be collect all these nodes in each component. So basically I want to find out a connected component that I can do using BFS or DFS, but then also I want to actually collect all the nodes in that particular connected component. All right, so because it's a graph, although it's a disconnected graph, I will find out all the connected components, because it will contain all the connected components. Even if every node is not connected to any other node, still it has that many number of nodes as like number of components, because each node is a component itself. So that is why now collect all nodes in each component using BFS. I will use BFS this time because BFS is more efficient in like visiting all the nodes as soon as possible, rather than doing it DFS. Like it doesn't really matter in this case, because DFS is not like doing any special thing for us. It's just visiting all the nodes of a connected component and just giving us all the values. So this will return us all the group of nodes that in that component, in connected component. This is how I'll write. Now third step is going to be step 3 would be find like increment the count. So we'll have like, let's say connected complete components. So this is going to be my variable. So increment this if all the nodes in the group, so in this group that we just found out, so this group right here, this particular group we are talking about, if all the nodes in this, basically if all the nodes in this group nodes, so let's say if this is U, so let's say, so basically the length would be K, so length would be group nodes. This K, basically all U in group, this group nodes, basically. So if graph and length of this value in this graph of U, so this will give me all the neighbors of U, and its length has to be equals to K minus 1. All right, so if this is true, if true, we will increment this right here. So increment this. So these are the 3 steps that will be giving us answer. And honestly, these are all simple steps. We know how to create a graph adjacency list. Then we also know how to run DFS or BFS on a given graph. And we will be doing it to collect all the nodes in the connected component. And once we are done with that, then we will be going over all the nodes in that group, to basically check if all these nodes, the neighbors list of all these nodes in my graph right here, of all the nodes that this group gives me, their length is equals to K minus 1. What is the K? K is the length of the group that we just collected using BFS. All right. So that will be all, and that will be a beautiful solution to implement, because all these steps are so clear. They're just, easily we can translate them to code. So as I said, we will create graph. All right, so let's have graph is going to be this default dict, we can call default dict of type list. It will be collecting the list of all the collecting all the neighbors. So for A and B in edges, so graph A's neighbor would be B, so I will append B to A, and then I will do the vice versa. I will append A to B's neighbor now. All right, so A will be appended to B's neighbors. All right, so graph is ready. Graph is ready. One more thing that I want to do is have a visit set. We have done the graph, right? The graph there. Maybe let's have a little gap there. Then I'm going to have a DFS right here. Oh, sorry, BFS. We will be writing BFS here, which will be taking a node, and it will be returning basically a group of this collected group of vertices in a particular component. But before that, let's just send in. So I will declare a variable called, let's call it complete components. Components. All right, that will be initially 0. Now I will run all the nodes. So for nodes in range n, and then I'm going to have a visited set right here. So I'll declare a visited set. It's going to be a simple set, and if this node not in visited set, all right, if this has not been visited yet, then we will call BFS on this node, and this BFS will be returning us group. It will be returning us a group of nodes. So group of nodes. Yeah, that's pretty good. So it will be returning us this group of nodes. We will do something with this group of nodes. What is that? We will be actually once we have this group of nodes, we will be here. We check if each U is a node in this group of nodes has its k minus 1 number of neighbors in graph. So what is k? Where k is len this group minus 1. Awesome. This is what we will be doing. Okay, too many things we have written, but anyway, this makes our things clear. But before that, let's implement our BFS. So BFS is going to be first thing, we'll have the queue. Let's append into our queue this node. Then we are also going to add that to our visited set. So visited dot add this node, and at the same time what I want to do is I will declare this group of nodes, right? So this node, I'm just going to call it group now. Okay, so initially this group, what I can do is I can add this node to the group right here, or maybe I can leave it like for our while loop to start off this. So while queue, this is how BFS is written. So I'll be writing like simple BFS, nothing complicated, and even this thing could be just turned into DQ, honestly, because it's better, right? Or maybe it wouldn't make like much of a difference. So let's take out the node. Let's call it q.pop. We're popping the value. Now this u, now we are going to visit all the neighbors of this u. Before that, let's add it to the group. Add it to the group that we will be returning. So append this u into the group, and in the end, by the way, we will be returning this group. Now for v is the neighbor in graph of u. Graph at u, all the neighbors are v. If this v not in visited, that means we will append it to my queue. So q.append to my q.append this v, and then also mark this visited. Add this v2. So this is a simple BFS. It's just this extra line that we have added to collect all the nodes in that particular connected component, by the way. And I will be calling these connected component right here. Each time this runs, that means I have a node with me, a fresh node that's not been visited, and when I run BFS, I will be running the BFS on this node, and right here it will be bringing me all the nodes that this node is connected to. So all the vertex that are connected to this. So it will be giving me this group. Now what I can do is I can basically check all these complete components. So what I'll do, I'm gonna work with this group of nodes, and before that, let's have k calculated. So k is len, and also this looks a little bit ugly, but like I hope it helps in some way of clearing things up. It's better to talk about like write your thoughts down, that what you plan to do, because it just easily translate then into a errorless code. So that's k minus 1. So k is like length of group of nodes minus 1. And for u in this group, so all the nodes in this group, if the length of all the neighbors of u in this graph, if this is actually not equals to k, then I'm going to have a flag here. We can call it is complete. Initially, let's mark it true, not false, true. And then if that node u, which is part of this connected component group, is not connected to every other node, which we are actually comparing, because if I am connected to, let's say I'm the node of this group. This group has 5 nodes, and I'm in that group. I should be connected to 4 other nodes, because I am not in my own list, right? I'm not in my own list because I'm connected to myself. So that is why we are checking if this is not its neighbors list is not equals to k, which in my case should be equal to 4. If this is not there, then I will mark is complete false, and I will break out of here. So break, and once I come out of this for loop, if this is complete, if this is true, then I can increment my complete components by 1, and then in the end I can just return the same value. All right, let me zoom out so that you can have a nice look at the entire code. So this was the step 1, by the way, creating the graph adjacency list, then visiting all the nodes in the graph. If that node has not been visited, that means I'm visiting a fresh component, fresh connected component. Visit all the nodes of that component using BFS, then this will give me a group. Now check in that group if every node is connected to every other node, and if they are not, then don't increment the complete components, otherwise increment it. So that would be it. Let's run our code. Let's run it. I hope there are no typos. All right, there are no typos because we are fucking legends, right? We are fucking legends. We have been grinding for more than 10 months now. 10 months, yeah. All right, so now let's write down the time and space complexity. Time and space complexity. Time complexity would be big of v plus e, number of vertices and edges. That's the usual, because you are visiting each node just once, right? Because this BFS does not try to visit like the node that has already been visited because of this line. You visit all the components, and then for space complexity, well, one component can be part of just one vertex can be part of just one group. So that is why this is also going to be same. Space complexity is going to be same v plus e, because you are creating for each vertex right here, adding it to the graph. Then you have visited sets. Visited set is going to be the time complexity of space complexity of v, but this right here, you know, is bigger because it also stores the edges. All right, so we're done. Boo. Going back to AlgoYogi, mark this solved, and see you guys later in the next problem. Until then, bye bye.